Hey, what's up, everyone? Welcome to Descriptive Chem/Lab Part 3. Today we're going to go over acids, bases, pH, salt solutions, and we're also going to touch on the metal reactivity series, but I don't want the title to be too long. So let's just get started. An acid or a base is going to be defined differently based on what definition or what model you use. And so there are going to be three major models that I want to go over. The first one is going to be the Arrhenius model. And so the Arrhenius model is the simplest and probably the oldest, I think. In the Arrhenius model, acids produce H plus ions in aqueous solutions, and bases produce OH minus ions in aqueous solutions. So what does that look like? For an acid, it's going to be in the general form HA is going to produce H plus ions and A minus ions. And you might notice that there's an equilibrium here. That little symbol between the HA and the H plus is an equilibrium symbol, and it just means that in the actual solution, you're going to find some HA ions, you're going to find some H plus ions, and some A minus ions, and the amount of each ions that you're going to find is going to be based on how strong the acid is. But we'll get into that later. I wanted to make a note of this form right here. That first form right here isn't really how it is. In reality, you're not going to be producing H plus ions. You're really going to be producing H3O ions, hydronium ions. And that's because the acid is going to be really reacting with water. And when acid reacts with water, it produces the hydronium ion and then the A minus ion. And so a lot of the times you might see the reaction being written like this, the one on the top, and that is purely for, simplicity. The second reaction is really what's happening. All right, let's take a look at some examples. So you can see hydrochloric acid on the top here produces H plus ions and then chlorate ions. And interestingly, you might notice that there's a forward reaction here and not an equilibrium. And we'll see why that is a bit later on. But again, remember that the real reaction is the one on the bottom. So hydrochloric acid reacts with water to produce hydronium and chlorate ion. But again, we simplify to the first one, for simplicity. And there are two more examples of acids in that form. So now that we've looked at acids, let's take a look at bases. And so bases are going to be in the form of BOH produces B plus ions and then OH minus ions. Here are some examples. Let me just erase that real quick. So LiOH produces lithium ion and then hydroxide ions, and then KOH produces potassium and then hydroxide. All right, let's take a look at the second model, which is the Bronsted-Lowry model. And so in the Bronsted-Lowry model, an acid is a proton donator and a base is a proton acceptor. So what does that look like? Acids are going to have that same form, HA dissociates into H plus and A minus. And so now we have some new vocab. The acid that we have is called the acid, and it reacts with a base. An interesting note about water is that it can act as both an acid and a base. So it really depends on the context of the equation to figure out whether or not water is going to be an acid or base. And it's going to produce a conjugate acid and a conjugate base. We're going to take a look at what conjugate acid and what conjugate bases mean a bit later on. But let's take a look at what bases look like. And so bases change a little. In the Bronsted-Lowry model, a base plus water reacts to produce the BH plus ion and then the OH minus ion. And so again, you have your base and you have your acid. And in this case, like I said, the water is going to be an acid. And then you produce the conjugate acid and then the conjugate base. And so what are these conjugate acid and conjugate base terms? Well, the conjugate acid is the substance that forms after the proton is gained. So conjugate acids are going to contain one more H plus ions than the base. And on the other hand, a conjugate base is the substance that forms when a proton is lost. And so you can create a conjugate base by having one less H plus ion than the acid. Let's take a look at the last model, which is the Lewis model. And so in the Lewis model, bases are electron pair donators and acids are electron pair acceptors. You can see a little model here where the nitrogen has an extra pair of electrons and it gives it to the H plus. So in this case, the NH3 becomes the Lewis base, and then the H plus is the Lewis acid. The Lewis model is sometimes helpful because it covers some reactions that don't involve bronsted-lowry acids and bases. And generally, we use the bronsted-lowry model for a lot of our acid-base problems. But do know that the Lewis model exists, and it does help to explain some of these weird anomalies that we find in the bronsted-lowry model or the arrhenius model. All right, let's take a look at strength of acids and bases. So let's take a look at strong acids first. Imagine you have a solution of hydrochloric acid. And you may expect that in there, you are going to find hydrochloric acid molecules. If you zoom really in, you might expect that you just find molecules of hydrochloric acid, but really that's going to be wrong. Since hydrochloric acid is a strong acid, it's going to dissociate completely. So in that solution, you won't find molecules on their own. Instead, you're going to find their ions, and they're going to be split up. And so if we write out the reaction, it's going to be hydrochloric acid is going to dissociate into H plus and chlorine ions. And then what's that part to the right? Equilibrium lies far to the right. So in any equilibrium, you're going to have reactants and you're going to have products. And based on however much of products and reactants you have, equilibrium is going to lie at a certain place. So if you have more reactants than products, equilibrium is going to lie to the left. And if you have more products than reactants, equilibrium is going to lie to the right. And so if equilibrium lies far to the right, then that means we're going to have a lot more products than reactants. In this case, you're going to have maybe a bit of your products reacting back into reactants. But in general, it's going to be mostly reactants turning into products. And that's why we use a forward reaction to depict many of these strong acids and bases dissociation. And so that means in strong acids and bases, the concentration of your acid is going to be the concentration of your H plus ions. And we'll see how that changes a little bit in bases, but it's essentially the same idea. So let's say you have a strong base. Let's say you have NaOH, sodium hydroxide. And again, you might expect them to be in molecules, but as you can guess, they're not going to be. They're going to be dissociated because they are strong bases. And so if you write out the reaction, NaOH dissociates into Na plus and OH minus, and again, equilibrium is going to lie to the right. And so we can write out that reaction as a forward reaction, because all the molecules here are going to dissociate into this. So the concentration of NaOH is going to be the same concentration as the OH minus ions. And so in weak acids and weak bases, you don't see this much dissociation. Instead, you're going to see maybe 1 to 10% dissociation. And depending on how weak the acid or the base is, it's almost negligible how much it dissociates. All right, so let's take a look at some examples of weak acids and weak bases. And so you have some strong acids and some weak bases, and I kind of would recommend you try to memorize some of these, but don't stress it too much. You'll probably get familiar with a lot of these as you practice and go on. And then so again, you have bases, strong bases, weak bases. I guess you just have to know them. All right, so let's take a look at the pH scale, and you may have come across the pH scale in your everyday life. But what it really is just a convenient way to represent the acidity of a solution. And it actually has a formula. So pH is the negative log of the concentration of H plus ions. And so let's take a look at an example to see what that really means. We're given that we have a 500 milliliter of 0.1 molar hydrochloric acid combined with 500 mils of water, and we're asked to find the pH of that solution. Well, so first of all, let's take a look at the initial concentration of hydrogen ions. We know that in 0.1 molar hydrochloric acid, we're going to have 0.1 molar hydrogen plus ions. And the reason that is because hydrochloric acid is a strong acid. So the concentration of HCl is going to equal the concentration of H plus ions. So we know that our initial concentration is going to be 0.1 molar. But unfortunately, we're not done yet, because we need to do a dilution. because we're going to be adding that 500 mils of water. So if you remember our dilution formula, it's going to be M1 V1 equals M2 V2. The initial molarity times the initial volume is going to equal the final molarity times the final volume. So our initial molarity is going to be 0.1 molar. Our initial volume is going to be 0.5 because 500 milliliters is 0.5 liters. We're trying to find our final molarity, but we know our final volume is going to be 1. Because remember, we're going to add that 500 mils to this 500 mils to produce 1 liter. And so M2 is going to be 0.05. And so now we can plug this value into our formula. So minus log of 0.05 is going to come out to about 1.30. And so that's our final solution. The pH of this solution is going to be 1.30. We don't just have the pH scale, we're going to have the pOH scale. And so in the pH scale, the values to the left, so values like 1, 2, 3, they're going to be highly acidic, and values like 11, 12, 13, 14 are going to be highly basic. And the pOH scale is the complete opposite. So 1, 2, 3 are going to be your highly basic ones, and then 13, 14, those ones are going to be your highly acidic ones. And so the pOH is the negative log of the concentration of OH minus ions. So what does that look like? We're asked, what is the pOH of a solution of 500 mil, 0.1 molar NaOH, and 500 milliliters of H2O? So again, let's take a look at what the concentration of the OH is going to be. We know initially we're going to have that 0.1 molar NaOH. And since NaOH is a strong base, we know that the concentration of NaOH is going to equal the concentration of OH minus. So our initial concentration is 0.1 molar. But again, you have a dilution because you're adding water to it. So 0.1 times 0.5 equals M2 times 1. It's very similar to the first problem. And so our final molarity is going to be 0.05. So our concentration of OH minus ions is 0.05. So remember, our pOH is the negative log of the concentration, so 0.05, and that means our pOH is going to be 1.30 again. So again, we have two completely different scales here, and if we try to calculate the second problem using the pH scale, we would get a really high number, probably like 13, 14, something like that. And if we did this one using the second scale, we would get a really high number too. Okay, let's take a look at some more interesting things about the pH scale. You might have heard that the pH scale is between 0 and 14. And same thing about the pOH scale. But that is wrong. pH can be negative, pH can go over 14. And so where does that 14 number come from? Well, the pH and the pOH is going to equal 14 at 25 degrees Celsius for any aqueous solution. So remember, pH scale is not between 0 and 14. You can have negative pHs, you can have pHs above 14, but pH plus pOH is going to equal 14 at 25 degrees Celsius for all aqueous solutions. Okay, let's take a look at an example. We're asked, what is the pH of a solution formed by mixing 45 mils of 0.1 molar nitric acid, 50 mils of 0.2 molar hydrochloric acid, and 55 mils of 0.1 molar acetic acid. Okay, so we know that we have HNO3, HCl, and acetic acid. And so you might notice for two of these, nitric acid and hydrochloric acid, these are going to be strong acids. But for the acetic acid, that's going to be a weak acid. And we'll see why that's important. Remember, in order to find the pH, we're going to need the concentration of hydrogen ion. And in order to find the concentration, let's first find out how many moles of hydrogen ions are going to be produced from each one of these. Since the nitric acid is a strong acid, we can determine the amount of moles that are going to be produced just by multiplying the molarity times the amount of liters. So our liters is going to be that. And so that means nitric acid is going to contribute 0.0045 moles of H plus ion. Let's look at hydrochloric acid. We have 0.2 molar times 50 mils, which is 0.05. So that means it's going to contribute 0.01 moles of HCl. And then, but for acetic acid, remember it's a weak acid. And a lot of times these weak acids contribute a negligible amount of hydrochloric acid. So for this one, we can just assume that it's going to be 0. So again, we need to find concentration. And concentration is just moles over liters. So if we add up our moles here, we're going to get that we have 0.0145 moles over our liters. So our liters, we know that it's going to be 45 mils plus 50 mils plus 55 mils. And that's 150 mils, which is 0.15 liters. And so if you do this calculation, 0.0145 divided by 0.15, our concentration of H plus ions is going to be 0.0967. So again, pH is negative log of, H plus. And so our pH is going to be, if we do negative log of 0.0967, we're going to get that our pH is right about 0.01. And that is answer choice C. And we are correct. So again, we figured out how many moles of H plus ions are going to come from each of these 3 species. And since nitric acid and hydrochloric acid are strong acids, then we can just multiply the molarity times the volume to get the number of moles of H plus ions. And then for the weak acid, we basically just assumed it was 0 because the amount that it actually contributes will still be negligible. And so we divided the number of moles by the number of liters to get the concentration, and we plugged that concentration into the pH formula to get the pH as 1.01. Okay, let's move on to salt solutions. So if you have a salt and you dissolve it in some water, depending on the properties of the salt, depending on what the salt is, the solution could turn a bit acidic, a bit basic, it could stay neutral. And so how do we predict what salts are going to produce acidic solutions, basic solutions, and neutral solutions? Well, in order to do that, you need to know that salts are going to be produced in an acid-base neutralization reaction. So what does that mean? Let's take a look at these 2 reactants. They undergo a double displacement reaction to produce a salt and some water. And so what does that mean? Well, if we are given a salt, let's say you're given the salt KNO3. You know that KNO3 is going to be produced with water. And so it's going to be the result of a double displacement reaction. And so AB plus CD is going to produce AD plus CB. So if we know our A is going to be K, and our D is going to be NO3, our C is going to be H. Remember, water is just HOH, and B is going to be OH. And so this fundamental idea allows us to figure out the reactants that produce a salt. And we'll see why the reactants that produce a salt are going to be important. So that means the reaction that produced this, or the reactants that produce this, are going to be AB. AB is KOH, and then CD, which is going to be HNO3. So using this like reverse double displacement reaction, we can figure out that the reactants that produce this are going to be KOH and HNO3. And so these are acids and bases. And the properties of these acids and bases, the reactants that produce a salt, are going to determine whether or not a salt is going to produce acidic, basic, or neutral solutions in a water. So the reactants that produce a salt tell us the acidity in the solution. If you have a strong acid plus a strong base, it's neutral. Weak acid plus a strong base, basic. Strong acid plus weak base is going to be acidic. And then weak acid plus weak base is a little complicated. Actually, let's go back to our previous problem to show what that looks like. KOH is going to be a strong base. HNO3 is a strong acid. And so from our little thing over here, we know that it's going to be a neutral salt. So, my bad. So KNO3 is going to produce a neutral solution when dissolved in water. And we figure that out by figuring out the reactants and then seeing that they're both going to be strong. Okay, so again, weak acid and weak base are going to be complicated. It really depends on certain equilibrium values, and I don't want to get into that right now because equilibrium actually is a topic. I think it's like Unit 6. Maybe I'll get into that then. But there's two more things that you need to know. The dissolution of strong acids and bases in water is exothermic. So if you dissolve a strong acid or a strong base in water, the water is going to get hotter, meaning it's gonna the acid or the base is gonna exert energy. It's gonna give off energy. And so what does that mean for the dissolution of salts? Well, it's a little complicated. You can't really tell based on what the salt is whether or not the dissolution of it is going to be exothermic or endothermic, but generally salts of NH4 plus are going to be endothermic. You're going to see a bit of practice in this in a bit later, but I just want to do a little metal reactivity series. And so if you have a metal ion and you put that in water, it's going to react differently. So some of these are going to be super reactive, and some of these are going to be highly unreactive. And the series goes like this. So platinum is going to be the least reactive, and the potassium is going to be the most reactive. There's this stupid acronym I found, and it really is the stupidest acronym I've ever come across. Please stop calling me a careless zebra. Instead, try learning how copper is. This makes no sense. Anyways, basically, it's good to know some of these. You'll see which ones are actually like pretty important if you just do a bit of practice. Like I would know that sodium is super reactive, and maybe if you are weird, maybe you'll learn this acronym on the right here. Anyways, let's just do some practice with everything that we learned. An element is a solid at room temperature, but soft enough to be cut with an ordinary knife. When placed in water, the element reacts violently. Which element is it? And so this is going to be our metal reactivity series. Let's take a look at each of the four choices. First of all, we have sodium. We know that sodium is going to be highly reactive. It's right here. And so sodium is a possibility because it says the element reacts violently when placed in water. So Na is an option. Let's take a look at magnesium. Magnesium is actually down here, and it's not like it's kind of reactive. It's not really that reactive, so we can cross that off. Copper is like way down. Where is it? Yeah, copper is like right here, so that cannot be it. And then mercury is right. Where is that? Oh, mercury is right here. It took me so long to find that. But regardless, it's not going to be reactive. And so the only answer choice that we're left with is going to be sodium, and that is actually the answer. Let's take a look at the next one. Which reaction is not exothermic? So remember, the dissolution of strong acids and strong bases are exothermic. So let's take a look at what these say. The concentration of dilute hydrochloric acid in water, that's going to be exothermic because remember, HCl is a strong acid. Dilution of concentrated sulfuric acid is a strong acid, can't be it. Dissolution of solid sodium hydroxide, NaOH, strong base, can't be it. And then dissolution of sodium bicarbonate. So sodium bicarbonate, NaHCO3, is actually a weak base. And so remember, weak bases are not necessarily exothermic or endothermic, but it's definitely not going to be exothermic because remember, those are going to be your strong acids and your strong bases, and sodium bicarbonate is a weak base. So it's going to be D, and we are correct. Next one, a 0.1 molar solution of which salt is the most basic? So remember, a salt is going to be basic in solution if it has a weak acid and a strong base as the reactants. So let's try to find out the reactants of all of these. NaNO3. And so you can pretty easily find them out by, well, to the cation, the positive ion, you just add an OH, and then to the anion, you just add an H. So that means our reactants are going to be NaOH, and HNO3. And so if you realize NaOH, strong base, strong acid, is going to produce a neutral solution. Strong acid plus strong base is neutral, so it can't be A. NaClO4. Again, you just add an OH to the Na, so NaOH plus HClO4. Strong base, strong acid, neutral solution, that can't be it. And then NaHSO4, NaOH, and H2SO4. H2SO4 is a strong acid, NaOH is a strong base, neutral solution, can't be C. And we're left with NaHCO3. So again, we have NaOH and then H2CO3. Carbonic acid, or H2CO3, is actually a weak acid. So we have a strong base and a weak acid, which does produce a basic solution. And so our answer is going to be D. And we are correct. I think we have one more problem. Yeah. Dissolution of which salt in water reacts in a decrease in the temperature of the solution. So decrease in temperature means endothermic. And if it really asks for endothermic, you kind of have to just remember that salts that are going to be endothermic are going to contain the NH4 ion. And so it's pretty hard to know whether or not a salt is going to be exothermic or endothermic just by looking at it, but NH4 plus is a pretty dead giveaway that it's going to be endothermic. And the only answer choice that has NH4 is going to be D. And that is correct. All right, that's all I have for this lesson. I hope you learned something, and I hope to see you next time for part 4.